So as stated, my name is Vannessa Campfield, and I work with Dr. Owen McDougall at Boise State University. Today I'm going to be talking about the identification of Propionibacteria inhibitors in Swiss cheese milk, contributing to complications in the quality assurance of Swiss cheese. Now, before I do that, I'd like to tell you a little bit about myself. I received my bachelor's degree in chemistry from Boise State University in 2018 and immediately began the master's program. I'm currently a second-year master's student. I'm hoping to get everything wrapped up and graduate this summer. I've been working with Dr. Owen McDougall in his lab for about 5 years now. And for the past 2 years, I've been working on the Build Dairy project. I also presented the information and research on this project during a 3-minute thesis competition and was an award recipient. So I'm pretty excited to tell you where the project has gone. So the production of Swiss cheese takes place in 2 general areas. First, we have manufacturing, where milk is pasteurized, starter bacteria and rennet are added. The curd is processed and pressed, and then there's a brining step. The second area is the ripening and curing of the cheese. This step includes a combination of storage rooms at different temperatures for specific lengths of time. These rooms allow certain bacteria to flourish, which contribute to the Swiss cheese characteristics. For example, Propionibacterium metabolizes lactate through a classic propionic acid fermentation, and that leads to propionic acid, acetic acid, water, and carbon dioxide. It's the propionic acid and the acetic acid that also give rise to that nutty sweet flavor, as well as carbon dioxide, which really is helpful and contributes to the eye formation. However, our industry is facing some challenges. Swiss cheese characteristics are graded by the USDA. Well, in 2018, we produced over 316 million pounds of Swiss cheese. The USDA downgraded 17% of our Swiss cheese. Since 2018, those numbers have only increased. This led to an industry loss of over $69 million. The downgraded cheese or challenges that we're seeing include blind or underset cheese. These have few to no eyes. O'Sullivan et al. Explained that this is due to a lack of propionic acid fermentation or a lack of nucleation sites for that eye formation to take place. This challenge alone causes half of all of our downgraded Swiss. We also see splits or severely cracked cheese. This is caused by excessive proteolysis as well as acid production. We see overset cheese, at times taking on a cabbage-like appearance with having a very thin layer of cheese between the eyes. This is due to excess gas formation caused by Clostridia bacteria. In addition, we also see collapsed or irregular eye distribution. This is due to incorrect eye formation during that ripening process. Originally, I was hypothesizing that organic acid profile resultant from the Swiss cheese microbiome correlates to cheese quality. Based on the data analysis between bacterial composition and organic acids, it has become very clear that the most significant factor in cheese quality is based on the microbiome variation, while organic acid profiles were less indicative of defects. For this project, I was able to obtain samples from a Utah processing facility, as well as an Idaho processing facility. Here forward, they will be referred to as Site 1 and Site 2 respectively. From the Utah facility, Site 1, I obtained samples of good Swiss and blind defect cheese. And every sample was run in triplicate. And from the Idaho and Utah facility, I received cheese with irregular eye distribution, overset, as well as split or cracked. Again, those were also ran in triplicate. To determine the bacterial profile, a cheese sample was processed using a Stomacher 80 paddle blender, and the DNA was extracted and purified with a microbial power food kit. I collaborated with the Molecular Research Core Facility at Idaho State University to accomplish next-generation sequencing and bioinformatics. To organize the vast amount of information received from bioinformatics, I used heat maps similar to Caitlin. I use them at each taxonomic level. When you look at a heat map, you have sample identification listed along the x-axis or along the top, and bacteria are listed along the y-axis. The colored areas in the body of the plot correspond to bacteria density. Using heat maps allows us to quickly visualize subtle variations in bacteria that occur in the specific defects and then compare those back to the good quality Swiss cheese. Well, how do we know which ones are important? We look at the statistics. Shown in this plot are the average bacteria across cheese samples. It also includes a 95% confidence interval for those measurements. This allows us to see which samples are statistically different from good Swiss cheese. Samples with high confidence of being different include blind cheese at 97.9%, as well as split and cracked from site 1, overset from site 2, and irregular distribution from site 3. Samples with lesser confidence, such as the split or cracked from site 2 at 78.6%, as well as overset cheese from site 1 and irregular eye distribution from site 1, are not statistically different. Now showing on the heat map are the bacteria that are statistically different for which samples. Since there are only 3 phyla with statistically different bacteria, it reduced the number of classes that needed to be analyzed. We follow the same procedure down through all of the taxonomic levels. At each stage, the focus is narrowed to include only the specific or significant bacteria. This allows us to see what variation is leading to the defect. This takes us to the genus level, which was the finest grained level analyzed. The following bacteria were statistically different in those samples. Well, what does this mean? Let's take a step back and look at the big picture. These bacteria are statistically different across both sites. It's pretty clear that these correlate to the listed defects. However, the presence of bacteria that are statistically distinct from good Swiss to the defect may not be the only indicator. In many cases, bacteria were statistically different at one site instead of 2. These particular bacteria are suggestive of a defect, but further studies are needed for additional support. Having exhausted the level of bacterial analysis that we can perform on the limited data we have, let's now take a look at the other focus of this project, which is the organic acid analysis. Organic acid analysis is completed using a high-performance liquid chromatography instrument, or HPLC. Liquid extract from cheese samples are ran through a silica support column in the instrument, and each component is then separated out. I perform this using organic acid reference standards to determine which acids are present. I used lactic, acetic, and propionic acid due to the actions of Propionibacteria. I used citric acid due to its contribution in defective eye formation, and butyric acid due to its presence in split and cracked samples, all coming from literature review. In this experiment, the HPLC was also coupled to mass spectrometry in order to definitively identify the individual components in each chromatogram, which allowed me to proceed with confidence in understanding what each peak represented. When compared to good Swiss cheese, blind cheese has slightly higher citric acid and lower lactic, acetic, propionic, and butyric acid. In overset cheese samples, compared to Swiss cheese, site 1 is higher in acetic and propionic acid, and site 2 is lower. And where site 2 has higher levels of citric, lactic, and butyric acids, we see that site 1 is lower. There is no agreement between both sites for overset cheese to be higher or lower than the good Swiss cheese for any of these acids. Compared against good Swiss cheese, irregular eye distribution samples have a lower amount of citric and propionic acids. Site 1 has higher levels of lactic acid, and site 2 has lower levels of lactic, acetic, and butyric acids. In the split and cracked samples, both sites have lower levels of acetic and propionic acid compared to good Swiss cheese. Site 1 has higher levels of citric and lactic acid, while Site 2 has lower levels of butyric acid. Using the HPLC, it has allowed me to visualize the organic acids in those samples. We can easily compare them against 2 other sites. It's inexpensive and it's quick. However, we also see a lot of scatter and variation, and the acid profiles are not as definitive as the bacterial composition. Turning the HPLC into a useful screening tool for defects requires further method development. A key factor in that development was using the mass spectrometer, but this limited the extraction solutions that could be used. This may be a trade-off not to make for future studies. In conclusion, the organic acids did not lead to a definitive indicator for potential defects as bacterial composition monitoring. In summary, with confidence, we can say that split and cracked samples are indicated by a decreased level of lactobacillus and an increased level of Propionibacteria, which is consistent with Daly et al. We can also say that irregular eye distribution is indicated by a presence of Clostridium and Candidiasis. These bacteria were statistically significant in both locations. This data is also consistent with O'Sullivan et al. These additional bacteria were statistically significant at 1 of 2 locations. This suggests that there is some kind of relevancy to the defect, but further studies are needed. And while we do have data concerning the organic acids, the results at this time are inconclusive. Moving forward, additional studies for this project include identifying unknown organic acid peaks by HPLC, because while they were not included in this first step of the project, they very well play some kind of a diagnostic role that could be helpful. A greater sample pool from both locations, both sites, would be very helpful, as well as longitudinal sampling throughout the ripening process. Personal next steps, I will be completing and defending my thesis over the summer, as well as publishing my results and graduating. And due to the in-depth skills, technical development, and support that I've received from the Build Dairy program, I've been extremely competitive in the job market, where I've started down a path of being an analytical chemist at Micron Technology. I could not have done this without Build Dairy. So first and foremost, thank you to the Western Dairy Center and Build Dairy. This has been a wonderful experience. I'd also like to thank Boise State University, our industry sponsors, and other collaborators. Are there any questions?
We do have time for questions. Any questions for Vannessa?
I have a question.
Yes, is this Tony?
Yes, I am. I have a question. I believe, correct me if I'm wrong, Swiss cheese, one of the culture of Swiss cheese is Propionibacteria bacterium. So it's responsible for the eye formation. I'm wondering if the defect is correlated to the amount of the specific culture we add intentionally or other wild bacteria.
Absolutely. So you are correct that the eye formation is predominantly caused or related to the Propionibacterium. If there is an excess of Propionibacterium, we tend to see an excess of carbon dioxide also in the cheese, which then relates to overset samples or really gassy samples. But if we have too little or a decreased population of the Propionibacteria, that's where we start to see more of the blind cheese, where there are not, those eyes are not formed.
Yeah, I understand your answer, but I'm wondering the defected the amount of let me think about the propionic bacterium in the defected cheese is the culture we add intentionally or not?
You know, just to clarify, are you asking if it's added during the starter culture?
Yes, yes.
Yes, there are a couple
Vannessa,
different strains.
Sorry, Vannessa, I think he's wondering if it's possible to have wild strains of propes landing in the cheese and interfering with the ones that we're adding. That's how I understood it.
Yes.
Okay,
yes.
Thank you, Eric. I appreciate that clarification. There are possibilities of having wild strains of Propionibacteria introduced into the system. You have natural Propionibacteria, but then you can also have different strains in the starter culture. And depending on these strains, they can also fight with the lactobacillus in the cheese during the ripening process. And lactobacillus can hinder Propionibacterium as well. So it is very specific to the strains that are added, which can then result in defects, yes.
Okay, thank you very much.
Thank you. Any other questions?
Yes, this is Don McMahon. I have a
Go ahead,
question. You mentioned that possible causes for blind Swiss cheese are no gas production by the Propionibacteria or lack of nucleation sites, which should be a kind of a mechanical cheese making issue. So does your data shed any light on that as far as the blind cheese? Do they, I'm just trying to think from your data, it showed that there wasn't an issue with not having the Propionibacteria there.
We are seeing the Propionibacteria in the blind samples, but we are not seeing consistency across both locations. And so we have a lesser confidence to say, yes, for sure, these are significant, or that they're not. And so I don't want to come across and say, yes, because it was seen in one location, we can agree to it. In that area, more studies need to be made just to give a better confidence and reassurance of that answer.
Yeah, and perhaps in light of having two possibilities, then those that are significantly different would say it's a problem with the bacteria. The other ones, maybe you could just attribute them to lack of nuclei.
Absolutely. And I appreciate you bringing that to my attention. This project focuses more on the bacteria, but there are definitely times where if you get too much air in the curd during pressing, you can have structural problems, and it can lead to some of the same defects as well. So there are definitely mechanical issues that can lead to a different amount of nuclei that are needed.
Okay, thank you.
Thank you.
So Vannessa, I have a question I'd like to ask you, because this came up in a conversation recently, that the silage, corn silage, had been used for feeding dairy cattle for a long time. And in the past, it was a natural fermentation, relying mostly on the bacterial strains that came with the corn. Basically drove a caterpillar over the top of the silage to drive the air out and get an anaerobic environment for the fermentation. But in recent times, they've started adding inoculants to that silage, which are lactobacillus strains. I wondered if you've had any conversation or any kind of ideas or thoughts about these silage inoculants finding their way from the feed to the milk to the cheese that could also be potentially interfering with the Propionibacteria.
That is definitely I won't say a hot issue, but a very relevant issue in the industry. In addition to using the silage, there are also types of Clostridium that are found that come across from that, which also lead to additional defects. I do know that in, I want to say Switzerland, they're also adding nitrate and lysosomes, which helps to prevent the growth of butyric acid bacteria in order to help the Propionibacteria kind of flourish and be able to do what it needs to do.